So today we're going to talk about preparing for multi-cloud operation and why multi-cloud operation is needed at all. So this is a bit unusual because we are doing this talk together. Why two speakers? So first of all, it was a little bit less for each of us to prepare, but we ended up preparing too much slides. So the talk might be long, but we'll try to do it fast. And actually, we wanted to show this problem of running multi-cloud from two perspectives. From business and high-level architecture, like why do we need to do it? What's the analysis behind it, behind the decision to do multi-cloud operation? And from implementations, detail like how exactly it can be done. So Oleg will talk about technical details. Oleg is a senior software architect at Intexsys. He has more than 7 years of experience, and he's working with the team who is actually behind the project of running multi-cloud operation and the hub.
And this is Konstantin. He's a founder of Intexsys and chief architect in our company, and he's the mastermind behind the multi-cloud thing, everything.
Thank you. So, agenda. We'll talk about why do we need multi-cloud, the challenges of why it's complicated, and obviously on addressing those challenges, how we can actually do it. So let's start from the initial state before the decision was made to work on multi-cloud. We are running one of the top 500 online retailers in USA. It's quite a large company. And we're running it on existing proprietary e-commerce platform, meaning that we're not running some out-of-the-box software. It's all custom developed by us. On a multi-component stack, you can see the technologies is mostly PHP and Symfony, and MySQL, which is important. We'll talk about that later. We're running 15 online stores, and from the business perspective, it's more than 1 million different goods sold on the stores, with a 300 million annual turnover. And last year we migrated the infrastructure to AWS. Before it was just like a bunch of racks in a data center, in a facility. Now it's all running in AWS. And we'll talk about it later, it's not only AWS. So back to the business and this number, so why these numbers are important. So if we split the annual turnover evenly for the year, the average would be more than $800,000 daily sales. So downtime cost, if we just do simple math, it's $500 per minute. But in reality, it's more because the sales in e-commerce are not spread evenly across the year. In reality, there is a high season and low season. High season for most of the e-commerce operation is during Christmas, and the time around Christmas. There are such events as Black Friday and Cyber Monday, which are very popular in the US where we're operating, and becoming popular here as well, as you know. So during such events, the cost of downtime, in our case, is up to $5,000 per minute. So keeping these figures in mind, let's talk about what happens what if AWS goes down. So you can say that it will never happen, but in reality it did. It happened, and many times. So this is the quote from a news website about what caused AWS outage for a few hours, which happened last year, maybe a year before. It was quite significant. So basically, the total losses of top 500 Standards & Poor's rating companies is estimated at 150 million. And that's just top 500 companies. And there are like thousands other companies which also lost some business, some money due to AWS outage. So what actually happened? The S3, the storage system of AWS, went down, and it caused the chain reaction of other AWS services going down and being not very stable. And it affected multiple availability zones and multiple geographically separate regions. So it was a huge problem. So, but why did it happen? Well, as usual, someone just pushed the wrong button. And Amazon, in fact, admitted it. They said that they had some automation script which was designed to change the number of nodes or whatever in S3 service. And an engineer doing some routine maintenance just mistyped, and instead of bringing down 10 nodes, he brought down like 1,000 nodes, and it caused the chain reaction because the system was not, it was designed well to handle outage of 10 nodes, but not 1,000 nodes. Maybe the numbers are not exact, but you get the idea. And here's the screenshot of a Wikipedia page listing, documenting all AWS outages. So it happens. It's not a very often thing, but it does happen. But even if AWS is fine, and everything goes smooth, we can have our own outages in the infrastructure. So we are running clustered systems like Elasticsearch and MySQL, but even these clustered services can go down due to a mistake by one of our engineers or just misconfiguration. There can be a lot of reasons why things can go down, even if AWS is operational. So, with the features of potential losses per minute and the problems of AWS outages or our own outages, we needed what's called a disaster recovery plan. So, what we're going to do if something goes wrong? So we evaluated like classic disaster recovery options. Restoring from backups, that's the simplest. We can have a snapshots of virtual machines and database dumps. And in case of an outage, we can spin up new virtual machines, restore them from snapshots, restore databases from dumps, and in theory, we can restore the service in some amount of time. Then there is a next step, it's a cold standby. A little bit better than just backups. It's when you have virtual machines configured, you have everything set up, but these virtual machines are turned off, and it's a cold standby. So in case of a disaster, what you do, you bring up these virtual machines, basically turn them on, and then you restore the most recent data, and it will be mostly database dumps, because static data can be on these turned off virtual machines. And then the next level is a hot standby. So the same, but virtual machines running. So you basically have a copy of your infrastructure somewhere. It's running, and you can replicate databases there, but it's just not serving the traffic. So, and then in case of the disaster, you need to reroute the traffic to this hot standby, cross your fingers, and hope that it will work. But since it's not running the traffic, things can go different ways. So with these options, we set the criteria, like how do we evaluate these options? Single point of failure or shared point of failure between primary operation and disaster recovery plan. So for example, if you're doing backup on AWS, and specifically to S3, which we know is not like that super stable. In case of disaster, this backup is useless. Also, if we're planning to restore the backup, just like on a different set of virtual machines in AWS, then again, AWS is a single point of failure. Time to recovery. This is very important. For us, if it takes 24 hours, it's not an option. Because on Black Friday, we will lose probably all of the yearly profit just in one day if we're not operating on one of these days. So we need fast recovery. And time to switching back. So if a disaster happens, we switch to a different infrastructure, but then the outage is fixed, we need to get back to our primary infrastructure. And in this case, we also don't want to affect the users and bring down the site just to switch it back. So this is also important. These are technical criteria, and then business criteria, mostly costs. How much would it cost to implement either of these options? And we need to look at the cost of implementation, which is kind of like one-time investment. We develop it, we invest, and then it's working. And then the maintenance cost. And the maintenance cost is how much effort it will take to support it, because obviously, even if you go with cold standby, hot standby, we need to update these virtual machines, we need to change something in the way how backups are done. So it has maintenance efforts. And just the cost of resources. So we will need to pay for storing the backups, for having these virtual machines cold standby, hot standby, running virtual machines, which is obviously more expensive. And then additional benefits. With either of these plans, what do we get in addition to just disaster recovery? Is there any business value in addition, or it's just disaster recovery? Because this will affect the decision. So here's the kind of summary of comparison table of the three classic options. So obviously backup is too long to recover, but it's relatively simple and low cost. Cold standby is faster to recover because we have the infrastructure with all virtual machines ready. We just need to restore the database, and in theory it will be operational. But we need to account for risk. So if virtual machines are turned off and not operating, when we bring them up, we may have some issues which we need to address. It's more complex, and the costs are medium. Well, on this scale of three options. Hot standby is probably the best. It's very complex. It has high cost because basically we need to run the same infrastructure somewhere else. And time to recovery is low. We estimated for us less than 1 hour. In theory it could be minutes, but the problem here is that if we're not running production traffic there, when we start running it, obviously something will go wrong. It's like when you first deploy a website or first deploy a new application, until you start running it and you have some experience, it would require some fine-tuning. So with that comparison in mind, we looked at the one more option, which is multi-cloud. So what is multi-cloud operation? First of all, it's not a disaster recovery plan. We're just running the system in multiple clouds in parallel with live traffic. So we treat it as production. It's not something, which we keep in the closet in case something happens, but it's just running real traffic. There is no single point of failure. It's completely isolated cloud by different provider. In our case, it's AWS and Azure. So they're completely isolated, and there's physically no single point of failure in the infrastructure. So it's almost instant recovery. So there is no recovery, it's just rerouting traffic. So the traffic is split, let's say 50-50 in normal scenario, but in case of the outage of one of the clouds, we're just changing this proportion. It's just changing one number. It's not some specific operation of the route. There is no failover and switch back phase for the same reason. So it has high complexity and cost, comparable to hot standby, but it provides better reliability. And it's continuously live tested. What I mean by this is that real customers are hitting multiple clouds. We treated it as production. We need to have monitoring, the same as for production and the same SLA. And we have real customer complaints. If something goes wrong, we have our own monitoring, so we will notice. It's always live tested. And there are additional benefits with this infrastructure. So basically we have kind of blue-green deployments, but not on the application level, but on the infrastructure level. So we can test various things and run infrastructure-related experiments, doing this just in one cloud. We can remove the traffic from there, change whatever we want, then send some portion of traffic there, and see how it works. We can also benefit from costs. So if the costs of different cloud providers are different, we can send more traffic to the cheaper cloud, and if the cost changes, we can send it back. So that's also a theoretical benefit. So you may wonder, why not just use AWS multi-availability zones? Basically all the same reasons. It can fail, even with multiple availability zones. Another reason, business reason, is a vendor lock. So if we're doing AWS with multi-availability zones, we are locking ourselves to Amazon. And as we are an e-commerce company, we're basically competing with Amazon. We are selling goods, and some of these goods are the same as the Amazons. So what if Amazon decides to, throw every e-commerce company out of AWS? In theory, it cannot happen, but you never know. So we want to be protected from that as well. Or what if AWS raises prices significantly? Same thing. And from complexity standpoint, running in multi-availability zone setup is similar to multi-cloud by complexity, because with multi-availability zones, you will have all the complexity inside AWS. But with multi-cloud, the complexity inside one cloud, let's say AWS, is simpler. You don't need multi-availability zones, it's just, a bunch of virtual machines, and it's all working. And the same in different clouds, like Azure or Google. Okay, you're shifting the complexity on the load balancing level between the clouds. But in reality, it's not that complicated. So overall, with the similar complexity, we get a better protection because it's just two clouds. Okay, so what are the challenges we had to address? These are specific to our case. Maybe in different applications, the challenges will be different. But first of all, pushing data to multiple clouds. So we have an infrastructure in the office, in the headquarters, which are just in US. So there is a physical infrastructure and applications basically preparing the data. Like for e-commerce store, it's products, variants, brands, categories, the content, which is developed in the office, and it needs to be pushed to the front and to the clouds where we're serving customers. So how do we push it to multiple clouds? Data synchronization between the clouds. So we have users signing up, we have users placing orders. And if a user happens to place order in one cloud, and the next hour or the next day, the same user somehow gets to a different cloud on the same website, the user would expect the data to be there. So we need to synchronize the data between the clouds in both directions. This is one of the main challenges. Deployment. So we need to deploy the application to multiple clouds. And as we are doing continuous deployment, the actual deployments releases are happening multiple times per day, so we need to orchestrate and coordinate it. There are dependencies, so there are front end of the website, e-commerce websites running in the cloud, but there are dependencies like APIs. So this front end uses the API, and we need to provide these APIs in multiple clouds as well. Scheduled jobs, like cron jobs. So then when you have one cloud, it's quite easy. You just set that this server will be doing this job and this server will be doing this. But now that the databases are synchronized, you need to think what will happen if one cloud goes down, where will we run these scheduled jobs. And obviously traffic balancing. So how do we send the customers to different clouds? Do we want location stickiness, so if the customer hits one cloud, he stays there? This is also one of the challenges. Monitoring, alerting. Basically, your monitoring and alerting multiplied twice, or if you're running 3 clouds, multiplied by 3, and so on. So, these are technical challenges, and I invite Oleg to tell you about the implementation details.
Thanks, Konstantin, for the great intro. And as you can imagine, doing multi-cloud is a bit challenging, and it even hurt people. So now let's talk about pushing data to multiple cloud. So as Konstantin mentioned, we have some backend office in our headquarters, where we have 100 people that are working on the content for our e-commerce platform. So in our office, we have a RabbitMQ cluster, which is basically mirroring data between two clouds. We have a single exchange, and because exchange can be configured to mirror or copy or duplicate message into 2 queues, we have 2 different queues for AWS, for Azure, and both clouds are consuming from their own queue. So this way we guarantee that both clouds are in the same condition in terms of content. Then the incoming traffic into clouds is free. So that is one of the reasons why we didn't do the multi-availability zones, because multi-availability zones, traffic between zones, is paid. Also, we have some sort of data which is located in our office, but our applications need to have access to that there. So we've configured a read-only application in both clouds. Now let's talk about data synchronization between clouds. This is probably the most challenging part that we've faced during the development of this project. We had to replicate relational data such as orders, and orders have ordered items and so on, users which have addresses, payments, and etc. between clouds. Then we are using MySQL, and we are not planning to change that because it suits us. So let's kind of discuss what kind of and how to replicate data between clouds. And before that, if we are running multiple clouds, we have master-master replication. So both masters in different clouds are available for write. So you need to make sure that if both clouds will receive a request, they will handle it. So initially, when our platform was using auto-increment for primary key, it suits us when we are running in a single cloud or single data center, but when we're talking about master-master replication, that doesn't work. So let's kind of imagine this thing. So we have John, we have Peter, and they will both create an account or place an order at the same time, the same second, which is likely unlikely, but let's imagine that. The request will be handled by different clouds. So what will happen? If 2 people place an order, what will happen? So your replication will fail because the primary key of both clouds will collide. So you have an order with number 1, you have in AWS, and you have the same order with number 1 in Azure. So the replication will stop. The only way to fix it is by manually resolving the conflict or ignoring the error, and your multi-cloud solution is auto-sync, so customers won't be able to see their order history or even sign in. So now how to avoid such situation? There are quite a lot of solutions on the internet how to avoid that. Here are 3 of them, which basically are forks of MySQL, but they're not that. So we have MySQL cluster, Performance DB cluster, and MariaDB Caldera cluster. But they all are using an approach called all or nothing. your application needs to handle any issues with the commit. The commit is the slowest, so the commit is slow as the slowest node in the group. It could be affected by network, certification tag, and local apply. And one more thing, we're not building a cluster. So this is a schema how this approach is working. So client is issuing an update, receiving an OK, it's in a single transaction. Then client commits the changes, and then MySQL or Grafana is sending the certificate with the global transaction ID to all the nodes in the cluster, and all the nodes in the cluster must apply the certificate or discard it. If everything is okay, you're successfully committed your changes and everything is fine. If certification fails, the transaction is discarded and you get the deadlock. So there are other solutions that we actually didn't consider them, but I found them on the internet. So you can adjust your primary key with the approach called even and odd. So each server has a server ID. So let's imagine you have server MySQL with server ID 4 and with a server ID 6. So you can adjust the auto-increment steps so that each next record would be +4 or +6, which is quite hacky, so we didn't even try to do it. The approach that we've taken is to implement primary key which will not collide. Many of you who are running large scale maybe know about what technology I'm talking about. So we've decided to go with the universal unique identifier. If for short it's UUID. First of all, it's a 128-bit number for 32 charts. Also, it's referred to as GUI in Microsoft products. Oh, it's Microsoft. We have at least 5 versions of UUID, which could be used in different cases. The first case is quite special. It doesn't have any RFC. So it's a nil UUID or null UUID, which is basically all zeros. Then the first UUID is generated based on time and node ID, and node ID is usually your MAC address of your server. The second UUID isn't used quite often, but it's basically an extension to the first with some DSI security. The third and the fifth UUID using namespaces to generate this ID. But third is using MD5 for hashing, the fifth is using HA1. And the fourth UUID is generating your ID using random children number. So it's quite unique to you. You have to probably generate 103 billion versions of this UUID to have a collision. And there's sixth version of UUID, which is unofficial because it doesn't have any RFC, but basically it's some sort of optimized version of the first version. So we've decided to use the first version of UUID because, first of all, it's time-based, so if we store it correctly, the sorting will not suffer. It can be optimized and stored in 16 bytes. The average rate that can be generated per node is 163 billion per second per node. So if we try to generate that amount of data on a single node, we may have a collision. One of the benefits of this version of UUID is that it can be tracked to a regional server. Because it's using MAC address in its code, we can track it. So, and in terms of MySQL, the trees will be more optimized, and it requires less storage for index. Because if you store 32 charts as a primary key, your index will expand very large, because we're using only 16 bytes. 16 bytes are everywhere. So this is a structure of UUID. basically, as you told, here's a MAC address, so this part will never change if the UID is generated on a single node. Then we have some information about type high, mid, and low, and reserve point with the clock with the 100 microseconds to avoid this collision and generate very fast. So how to achieve optimized UID? First of all, because it's time-based, we can reshuffle a few blocks. So we get the third block, reshuffle it in the first block, and then we take the middle time and the high time and change the location of them. Then we get the binary stream, which is 1 byte with bookx, and it's 16 bytes. But conflicts are still possible, but no more with primary key. The conflicts can be caused only by other unique keys. Another but it's highly unlikely. Here's why. So normal replication is done less than a second. And usually customers that are not botnets cannot do requests so fast to multiple clouds to get this, to break our replication. So now let's discuss what kind of data we need to replicate. As Konstantin mentioned, we have a data that is prepared in our office, and there is data that is generated by an end user. It could be customer or a server, if server stores logs in MySQL. So there is data that is generated by customer, and something is pushed by us to a cloud. So in order to maintain replication between clouds, we need to sync only the data which is generated by end customer. So here's a brief idea how to do database migration when you're running multi-cloud. First of all, there are a lot of articles about how to do zero downtime deployment, zero downtime migrations. And here are like 2 points that are more general. Avoid table locking, and in MySQL you can use a so-called online DDL, which is does not lock your table and does in the background, and only then it swaps and no data. Do not deploy code before your column exists. Well, I think it's clear. Always think about backward compatibility for database. Because rewriting database, it's not like rewriting the code. It's painful. Because your data may be already collected and you don't want to lose that. It's very complicated. Run drop and rename only after you are fully satisfied and your code does not rely on the exact naming, or it can handle the difference between naming. As a general rule, at least for us, if we have a huge alter, and if we want to alter a huge table which is more than like 10 gigabytes, do that manually because it's more predictable. And always remember, when you develop something, you are running multi-cloud. Another safety point that we've implemented for our developers, we've created separate users with different type of access for different type of tables. So there's one user which can alter the tables that are populated by customer. There is a user which can alter the table which is generated by us. By doing this, we've split our migrations into 2 categories. Let's call them local, which is not synchronized, and shared, which is synchronized. And then remove the data definition language permissions from your main user, which is used for reading your data or writing your customer data to your database. And another key that make sure before running a second deployment to another cloud, make sure you make sure that your second unified master is 0. Now, how to deploy to multi-cloud? Well, here, nothing actually changes from the usual deployment, but you need to make sure that your application is called agnostic. So in our case, we are deploying to AWS and to Azure, but we can deploy to Google Cloud easily because we do not use cloud-specific functionality, and we don't need to maintain that. Also, make sure that your application is not aware about the host names of your cloud, because as Konstantin said, we will have a blue-green deployment, and host name can change. So your application must be able to deploy to different hosts without even knowing where it's deployed. Store your configurations in environment variables. Well, this rule is taken from 12 factors. It's a great website where you can read some best practices. Well, basically because you can easily change the variable and you don't need to redeploy your application. As an example, you are upgrading MySQL. You just create a new MySQL, you just change the environment variable, and the traffic goes to a different MySQL. Do not deploy your application to all clouds simultaneously. The only reason why not to do that is because you need to have a fallback. If you deploy something in AWS and it magically is down, you need to have a fallback so you can easily switch traffic to Azure. So at the same point, you'll always have two versions of your application. So that's why think about backup compatibility. Now, since we're running front-end heavy applications, you need to think about your assets on front-end. So here, you need to figure out the assets lifetime, because browsers tend to cache your files for better performance. And you need to take that into account. So if you deploy a new version of application, the JavaScript that was cached by the browser must be able to work with your application. So as a general rule, you must have a few versions of your assets stored for some time. Same about backup compatibility. Well, JavaScript is, because it's cached by browser, you need to think about this even more, because reverting JavaScript is painful. So if you persist some data into customer space, it's a cookie local storage or any other storage which is stored on the browser, you need to make sure that this data is also compatible. The general rule: always monitor your logs. If a customer uses Firefox, he visits your page, he will have a lot of errors. You will see that in your logs. If, I know, our favorite Internet Explorer, you will see that. So this is kind of our lifetime of our assets. And as you can see, here we've deployed the new code. Here it's growing, and then at some point we'll deploy another code. Let's call this one here. And you can see the request, which is casting to CDN. It goes down, down, down until, so it's 5 days long. So we need to have our assets working for 5 days, even if we have 10 deployments per day. So it's quite a lot. Now let's talk about SRE. You need to have distributed crowns. Because if you configure your cron on a single server and this server goes down, you lose the crowns. You lose the ability to run your jobs. So scheduling must be delegated to independent application, where you can configure your clients, and this application must handle your virtual machine dev and can easily load balance and switch job path to a different node. There are at least 2 solutions that I know from open source. One is from Mezzas, it's called Kronos, and another is dcron. So, other facts about what we had to do during this project. We've upgraded our MySQL twice in 6 months, from 5.5 to 5.7, and recently was from 5.7 to 8.0. So So, and the key difference and the key goal of this upgrade was in 5.7 is to have an ability of GTID, which stands for Global Transaction ID, and channel replication channels. So in MySQL 5.7 or even from 5.6, you are able to replicate your data from multiple sources, and you can easily control or turn out this replication by using channels. And we upgrade to 8.0 only because of filter replication per channel. As I told, we have data that we need to synchronize and data that we do not need to synchronize. Before MySQL 8 replication, you didn't have an ability to configure a replication filter per channel. But in MySQL 8, you can do that. So we filter the tables that we don't want to replicate, and the replication is replicating only data that we need. So GTID stands for Global Transaction ID. It's used for consistency. Many who've done DevOps or even ops only may know that when you try to configure your slave for your MySQL, you need to specify a file position of a binary log. But using GTID, it's super easy to spin up your new machine. And with auto position, which can be on only with GTID, MySQL single handles this positioning. So, brief summary. Use UID to avoid conflicts with the primary key. Even if you are small right now, think about it for the future, because migrating from usual primary key after implementing UID is very complicated. It's very hard. We spent like maybe 6 months to do that. Determine the data you need to sync between your clouds. Monitor your application with all possible tools, because you need to react fast if it goes down. Use distributed cronks for your scheduling job. Monitor everything, including your CSS. And remember about the CAG theorem, which is stating about consistency, availability, and tolerance. So, the CAG theorem says that you cannot guarantee two things you cannot guarantee all at the same time. So it can be only consistency or availability, but you may be affected by tolerance. It can be availability and tolerance, but not the consistency. So to recap, when all the above is done, we need to implement traffic between two clouds, traffic balancing between two clouds. And Konstantin will continue his talk about this balancing.
That's the last step. Just to send the traffic to two more different clouds. So to do the traffic balancing between clouds, we're using several components. It's DNS weight-based load balancing. We're using the CDN combined with WAF, which is Web Application Firewall. And we have rules engine provided by CDN running on CDN edges. And I will show you a diagram and explain how it works. Not sure if you can see it, but the idea is the following. So then the request comes for a website. It's sent to CDN, where first it's processed by Web Application Firewall. So if it's blocked or some known vulnerability to the WAF, it just blocks. But if it's a normal request, then we have the rules engine on the CDN side. So the rules engine on CDN is doing basically two simple checks. First, it checks if the request has a cookie, a special cookie which we use for location sticks. So if the request doesn't have a cookie, meaning it's a new customer who just opened the website, the request is sent to a backend which has a DNS hostname of like balanced-site.com. It's a weight-based DNS record, which means that the record is resolved to different IP addresses, if we simplify that. And we can control the proportion. So with DNS provider, we can say that 90% of requests are resolved to an IP address, which is like AWS site.com, whatever the IP address is. And 10% of requests are resolved as Azure site.com. And then the CDN passes the request to this backend, so it goes either to AWS or to Azure. The response has the set cookie header, so it sets the cookie if it comes from AWS, the cookie will have AWS inside it in the value, and the same for Azure. So then the next request comes, it has the cookie, and then rules engine on the CDN is checking the value of the cookie, and based on the value of the cookie, it's sending the request directly to AWS site.com or Azure site. But then there is another trick in the bottom of this diagram. So what happens if one of these clouds is not working, or our infrastructure in one of these clouds is not working? So we have independent DNS-based health checks. So the DNS provider is doing the checks to see if a particular cloud or our endpoint in this cloud is alive. It's not like a ping or simple check. We can configure the DNS provider, we can configure what we want to check. We can send HTTP request, check the response, and this HTTP request can actually trigger some other health checks inside the cloud. So what happens if the DNS provider detects that it's down? It's just dynamically changing the resolution of the hosting. So if AWS is down, then AWS site.com will actually return the IP address of Azure. And in that case, the customers, the users, already have set a location stickiness cookie, they will be redirected to a different cloud. But then the first cloud is backed up, they will just go there. So this is not that complicated in reality to set up, but you just need specific providers for DNS. There are plenty of them available, and most of the modern CDNs can also provide that. So basically what you need is a rule engine on the edges, because with CDN we are avoiding single point of failure. CDN is decentralized, there are a lot of edges, so if one of the edge goes down, it will just route traffic to a different edge, and the rule engine, which does these two simple checks with cookies, is working on every edge of the CDN. So this is how we route the traffic between AWS and Azure. I just need to send one disclaimer that it's currently in alpha testing, but it's working and showing great results. So we're going to launch it in production, and basically launching it in production will mean just changing the weight-based DNS. Right now we're using our own record for internal testing. So this is it for traffic routing and the summary. So first of all, not everyone needs multi-cloud. You need to find your reasons, and you need to understand why you want to do it. So our reasons mostly were disaster recovery and mitigating potential risk of huge losses in case of outage. So another popular reason for going multi-cloud is when you have users in different regions, and you want to serve users from the closest cloud to where the users are. It's not our case because most of the users are just in US, but still it's a valid reason. Anyway, doing multi-cloud is not that easy, it's challenging, and it's also costly because in any case you are paying for the second copy of your infrastructure, at best. But it's doable, and even with quite regular stack of technologies like just PHP and MySQL, you can do that. It doesn't require some rocket science or super complicated technology switching to different database engines or something like that. It can be done with plain technology, which you're using today. This is it. If you have any questions, Oleg and I will be happy to answer. Thank you. what, sir?
The user recognition system.
User recognition system?
You mean the sign-in? Yes, I think we are using email. At the moment, we are using email.
Yeah, because you have the multi-cloud, and at the time of user registration, if two persons are using same email ID at the two different cloud,
Right. It's possible.
it's hypothetical, but
Yeah,
it's
it's
possible.
hypothetical, but it's possible if in case of some data breach on different servers, someone can still figure out the schema how to do that. But it's quite unlikely. Plus, we have the fast solution for using the password data breaches. So if someone is using your password and it was breached, then we block the account, or even disallowed you to sign up. So we have even if there's a data breach, usually the sign-in happens by using the botnet, some sort of, and we have reCAPTCHA, invisible reCAPTCHA. So, and now we are implementing some sort of two-factor authentication. So we are trying to secure our customers as much as we
Yeah,
can.
but the question was about just the uniqueness of data. Yeah, but that's why we do location sticking. So one user won't be able to do that, but but if it's a botnet, it won't break anything. It just, the record will be discarded after the application. We have special processing for that.
How many VMs you have for a product, to run the product? How many VMs?
In one cloud, it's probably 200 VMs.
And is it one MySQL cluster, or do you have?
So we have multiple clusters, but specifically for front end, it's one MySQL cluster with customer data. So we have this customer data which is being synchronized, and we have other local data which we are just pushing from the office to multiple clouds, but it's redundant. So yeah, we're operating multiple MySQL clusters, but this multi-cloud is just one cluster.
What if database in one location fails? Do you will redirect all the queries to another location?
Well,
Continue if you want to.
yeah, sorry. So if the database in one location completely fails, then the health checks, then the site will be down in this location.
So the whole site is redirected, all the traffic to another one.
Yeah, it will be just routed to different cloud.
Or we can easily do a switch to using hot standby, because we usually have redundancy. We have first master and second master.
Inside the
cloud.
one
So,
cloud.
Another question, how do you aggregate your logs?
it's a great topic. I don't see a Sergey here.
I'm here,
I see
yeah.
him.
I can tell you.
This is my colleague who implemented actually a log aggregation cluster, which is using at least 20 nodes of Elasticsearch. So we use the LK stack. It's working fine for our traffic and our logs, because as an example, our backend is generating 60 gigabytes of
A lot.
a lot. Yeah, so somewhere around 16 gigabytes of logs per day.
And I guess you have some dashboards that you solve.
Yes, so it's ELK, Elasticsearch logs-Kibana, and we have multi-cluster Kibana, so basically it's connected to multiple Elasticsearch clusters, so we can see the logs from different locations in one dashboard.
Is it in the same clouds, or do you have that here?
It's actually distributed too. It's located on, I guess, 4 data centers, including our own.
Yeah, including the office.
Yeah.
So worst case, if the one cloud is completely down, we won't see the logs from that cloud. We are not replicating the logs, obviously, it's just, doesn't make sense. But we'll still be able to access the logs from whatever is working.
Since you have the same infrastructure in different clouds, can you share how that costs compare?
So right now it's not proportional, but based on preliminary analysis, the costs between AWS and Azure are plus minus the same. So, and even if they're changing cost, it's funny because I'm subscribed to to their news, and it's very funny, you know, Amazon sends you an email that they dropped the costs for whatever, for storage or for some instance type, and 2-3 weeks later, there's the same email from Azure that they match the costs or go even more. So it's comparable. Obviously they are competing. I mentioned in the slide that in theory we can benefit from cost saving if the price is different. We are not doing that at the moment, but it's possible.
You have some plan in case if DNS provider fails?
Sorry, say it again?
You have some plan in case if DNS provider fails?
Well, DNS provider is distributed, so it's not just like one DNS server somewhere.
So it can fail.
It's distributed.
It's multiple providers, or?
It's distributed network of DNS servers. It's the same provider, but yeah, it can fail as everything.
Like AWS, it also distributed or replicated?
No, the difference is that DNS provider doesn't run the data centers. They just have DNS servers in different clouds and different data centers. So they are more resilient by that nature.
Still, they have technician who can push the button.
Yeah. Well, we cannot protect from that.
What if the internet fails?
Everything fails.
Maybe one last
Yeah.
question.
Maybe
The last question, what fails most often, AWS or Azure?
Well,
I know the answer, but
Well, what is the answer?
what's
Azure,
your,
of course. What? Azure, of course.
Azure, of course.
well, we don't have enough statistics because with AWS we fully migrated last year, but we've been using it for maybe a few years, and we experienced these outages. With Azure, we started probably half a year ago, late last year, and we haven't noticed like any major outages in Azure since then. So, but it's it's just
You mostly provision virtual machines, right?
Yes.
Not AKS, just virtual machines.
no, not yet. So
Storage.
virtual machines, storage.
There's something, yeah, I actually don't know, but when usually something fails on cloud provider side, does it fails like on all the regions, or? But because I'm thinking maybe instead of choosing another cloud provider, you could just choose AWS but from another region, right?
There was a slide about that. Even though the availability zone usually fails, there were cases when the whole region fails.
Okay, okay. Yes.
Not only because of that, because with the same, as I don't know, maybe you missed the slide, or with the same level of complexity as setting up multi-availability zone setup in AWS, we can do multi-cloud, which is better.
Yeah.
Okay?
Okay. Lots of questions. Did I get it right that the only traffic between two providers is replication of single database cluster?
Basically, yes. Well, in reality, it's something else, but the main traffic within clouds is just replication of the database.
And the last question, which engine do you use in Microsoft?
Engine in the DB.